it can get there when you're dealing with trig and logs and things like that. All right, so you can read through this stuff, but I don't know. I mean, it's all textbooky, so I don't know how helpful it's going to be, at least until you get to the inwards part. Derivative of the outside times the derivative of the inside symbolically. dy dx is equal to dy du times du dx. The idea being that if I multiply these two fractions, the du's would cancel out, and you would be just left with dy over dx. So if you're given two separate functions, y in terms of u and u in terms of x, you could actually just follow this blueprint here and come up with dy dx. The big challenge is going to come in when you're not given it in terms of u. All right, and we'll cross that bridge in a couple minutes. All right, so we have y equals u cubed. I need dy du. And that would be what? 3u squared. They also gave us u equals 2x squared plus 1. From that, I need du times du dx. We'll do the multiplication in a minute. Du dx would be what? 4x. All right, the last component, once you do all this, what we have already written down, once you have all that, the rest is easy, because dy dx is going to be equal to dy du times du dx. So we're taking this and multiplying it by this, but not in symbolic form, not the dy, literally the dy over du and the du over dx, but what they correspond to. All right, dy du is 3u squared. Du dx is 4x. So that's one form of our derivative, 3u squared times 4x. We can clean it up a little bit, but the issue here is I need dy dx, which means the derivative of the y function in terms per unit of change in x. So in terms of x. So the y function with only variable x. That u is out of place. That u has to go. All right. So I need to replace that u with some expression that contains an x. What would that expression be? What is the relationship between u and x? Two x squared plus 1, exactly. U, it says it right here. Well, it says it here first. U and 2x squared minus 1 are the same thing. All right, I rewrote it here, but still, it's very easy to lose sight of that sort of thing. Because I have 3u squared times 4x, and I'm like, okay, well, what is u? Well, it was there the whole time, staring in the face. So I'm going to replace the u with what it is in terms of x, and that is 2x squared plus 1. All right? So that's kind of a weird thing to think about, because what that's telling me is that if I had done my substitution from the beginning, that looks pretty awful. If I had done my substitution right from the beginning, I would have had a composite function y equals 2x squared plus 1 raised to the third power. Just by replacing the u with what it truly is in terms of x. What I just got from this is the derivative of this function. If I were to take the derivative of y equals 2x squared plus 1 cubed, I would get this as a result. All right? So let's just do a quick side by side on that, or maybe one above the other. See if we can learn something here. So y equals 2x squared plus 1 cubed, and its derivative, dy dx, was equal to 3 times 2x squared plus 1 squared times 4x. All right, so if you kind of cut out the fluff a little bit, all the intermediate work, you do your substitution in the beginning, you could still come up with your derivative. It's just a little trickier to see. All right, so if you don't see it right away, that's fine. Clicks for people at different times is one of the quirky parts about this course. So you can get to the derivative of this function without doing any of this other work. The shortcut rule involves us taking the derivative around the inner function. All right, so what I would say is, all right, yeah, there's a 2x squared plus 1 here, but, well, pretend it's just some function, some unknown function. So I would say something raised to the third power. So forget about what's written there. If I said, what is the derivative of something to the third power, what would you say? 3 times something squared, right? So something to the third power, 3 times something squared. Okay. Something to the third, 3 times the something squared. Where do you think the 4x is coming from?
The derivative of something.
The derivative of the something. All right. So take the derivative around the something, and then multiply it by the derivative of the something. Right? There's a lot of weirdness in what I just said, so it doesn't always kind of resonate with people the first time through, but it clicks eventually for everyone. It's just a matter of time. So we'll do it the long way and we'll do it the short way for each problem. And then eventually down the line a little bit, we'll just do it the short way. But we're not going to rush into just solely doing it the short way. And honestly, I mean, there are plenty of folks who totally understand how to do it the short way. You know, you get a lot of experience with this. Totally understand how to do it the short way, but there's more structure to doing it the longer way. They know they're going to get it right, and they don't want to take any chances, so they just always do it the longer way. Nothing wrong with that either. All right. So I have my y function here. 2 plus, I'm going to write the u as, instead of as a radical, I'll write it as u to the 1/2, where u is equal to x cubed plus 1. So what's my dy du? This is the part where you tell me the answer. 1/2 to the negative 1/2. All right, and my du dx? 3x squared. A little easier for that one. All right, so I have my dy du, my du dx. Now I just need dy dx, which is dy du. Crikey. Okay. I'll fix it. Hold on. All right, so dy dx is the same as dy du times du dx. All right, so for now, this blue stuff here is just the definition. That is the chain rule. But down the line, you'll understand where this sort of comes from. All right, so I know what my dy du is. It's 1/2 u to the negative 1/2. I can rewrite that. I know my du dx is 3x squared. My derivative should only be in terms of x, so I want to swap out the u for what it is in terms of x, and they tell us flat out here that u is x cubed plus 1. So I'm going to replace my u with an x cubed plus 1. All right. So now, that's the longer way. I'm going to take these two functions, put them together, write it as a composite function. Instead of the radical, again, I'm going to use the power of 1/2. The 2 is irrelevant when I take the derivative. All right, it's constant. Derivative of a constant is equal to 0. So I know I don't have to worry about that at all. That just tripped up on me.
And you always write it in terms of y.
Y in terms of x.
Okay.
All right, so the only one that I care about, the only function I care about, or part of the function, I guess, would be this one. All right, so I'm going to take the derivative around the inner function. So ignoring my inner function, I have something to the 1/2. The derivative of something to the 1/2 power would be what? 1/2 something to the negative 1/2 power. And you can see really that the u is the something. The way it was set up, they told us what the something was. It's the u. All right, so this longer approach is really just us detailing what that something term is or expression is. All right, then I take the derivative of the something, which would be what? 3x squared. All right, so definitely quicker. I mean, you still have to do the substitution, replacing u in your original function with what it truly is. But then once you get to that form, it's definitely quicker to come up with your derivative, but it requires some thinking. And also, it can get a little messy because depending on the nature of the function, we're only dealing with polynomial and rational functions so far, or radical functions, sorry. What if it involves trig or logs or things like that? It could get a little crazy. What if there's a function inside of a function inside of another function? That usually happens with trig functions. So there's stuff that we have to work towards, but this is a good place to start. Because we have to pull out what we think the inner function is. All right? So what we want to do is identify what expression is keeping your original function from being just a parent function itself. All right? I would like this, if I had control over the situation, I would like this to be y equals a sine of x. That's really easy to work with. I don't have y equals a sine of x. I have y equals a sine of this funny business here. All right, I don't want that there. If I could just remove that and make that something simple, then this would be easy to find the derivative of. So what I'm going to do is I'm going to remove that and make it something simple. All right, I'm going to make it y equals the sine of u, where u is equal to x to the 4th plus 5. All right. Yeah, because if that wasn't there, it'd just be a simple sine function. We know the derivative of sine is cosine, so dy du is the cosine of u. Du dx, you've asked the same, or different variations of the same problem like 4 times already. 4x cubed. So dy dx would be the product of dy du and du dx. dy du is cosine u. Du dx is 4x cubed. And then I just have to replace the u again with what it is. In this case, x to the 4th plus 5. All right. So then you'd have to ask yourself, does that coincide with what I was saying in terms of the shortcut on the previous page? All right. I have an inner function, so the sine of something has a derivative of the cosine of something. The derivative of that something is 4x cubed. All right. So even though it's a trig function, it still follows the same idea. But let me hop on down to number 7, because 4, 5, and 6 are things that you can handle based on what we've gone over together. But 7 and 8, yeah. So we have cosine of 4t squared, and the whole shebang is then raised to the third power. That's what it means when you put the 3 after the cosine, is that whatever cosine is of is going to be raised to that power, whatever that power happens to be. So a nicer way to write it, or at least a more understandable way of writing it, this actually is the nice way of writing it, would be cosine of 4t squared cubed. Alright, so earlier I was talking about the chain rule only getting more challenging depending on the type of function you're dealing with and how many layers you might have. So a function within a function is not too bad. Put a function within a function within a function and get a little messy. So here, under normal circumstances, I would like it to just be maybe cosine of u, or maybe u to the third power. I definitely don't want cosine of u to the third power, because that's a mess, right? So what I'm going to do is work outside in. If I could put this in its simplest form, the simplest parent function I'd be looking at is something, we've got a big something here, but something raised to the third power, all right? So I'm going to write this as y equals u to the third power, where u is equal to the cosine. Well, that's the thing. Normally I would say cosine of 4t squared, but that's not a parent function. So I got a little bit of an issue here. Cosine of 4t squared, that's just as challenging to figure out as, you know, the cosine being raised to the third power. So what I'm going to do is I'm going to create a second variable, cosine of v. You don't have to use v, you can use whatever you want, where v is equal to 4t squared.
How come you're just allowed to create variables?
You can always create variables.
Whenever it works?
Whenever it works, whenever it suits you, even if it doesn't work, you can always do it, yeah.
How come you can use u in the problem? Like,
Say that again, sorry.
it's funny. Like, there's no u in the equation. I'm just confused.
We're creating a u to take the place of a complicated part of the expression.
Oh, so we added u in as well.
Right, just like we did in the last problem.
Okay. Because that's what I thought, but then you said we can create v, so I was like, what's
Yeah,
the-
because we have two things that are making this complicated.
Okay.
Yeah, if this were just cosine of a single variable, I'd be a happy camper to some extent, because then it's a parent function for cosine. But that cosine function itself is being raised to the third power, making it part of another function, which is a cubic function. So we have to account for both of those. Now, if you kind of work backwards, replace the v with a 4t squared, and then take that entire cosine of 4t squared and use that to replace the u, you can see how that gets you right back to where you started. All right. The idea is that I can take the derivative of these three parts very easily. dy du, which would be 3u squared. du dv. What's the derivative of cosine of v? Negative sine of v. And dv dt which would be what? 8t. All right. Now what I'm looking for is dy dt. Will I get that if I multiply these three things together?
No. Does it cancel out?
It does cancel out, yeah. Because if I multiply these two together, the u's, the du's will cancel out.
Yeah.
And then I multiply these together, the dv's will cancel out. The only thing that's going to remain is dy dt.
Yeah.
So I have my three components. This one, and this one. That would be my derivative, just not in the best form, because it needs to be all in terms of t. So I have to do some reverse substituting here. So 3u squared, well, u is cosine of v. V is 4t squared. The last part, the AT, that's fine as is. I'm almost 100% there. Only in terms of t, only in terms of t. This has a v in it still. The v has to go. V is, again, the same as 4t squared. So I could do my substituting.
Make that one sound right.
You can, you can. Again, huh? All right, let me kind of exaggerate this a little bit. This is the same as saying x times 3x minus 9 cubed. And it's for questions like this where you have a little bit of extra motivation to get to know the shortcut approach. All right. What is that? Multiplication. When you multiply two things, what do you get as a result? A product. So what technique should I be using? The product rule. All right. Which of course requires you to know the product rule, which is why we spend so much time on that.
Oh, right.
Right, it's the first function multiplied by the derivative of the second function. So I need to get the derivative of the second function in there. So I'm going to leave a blank because that's going to be easier said than done. Plus my second function in its original state times the derivative of the first function. What's the derivative of the first function? 1. All right. Won't be that difficult if I can figure out what goes in the blank. All right. So what I'm going to do is I'm going to create just a new expression here because that's what I need to figure out. So let me just write y equals 3x minus 9 cubed. And I'm going to figure out the derivative of that just kind of in, side work. All right. And I'll do it with the y's and u's. So y would be equal to what? Because I need a y and I need a u. The u should be the inside function. So how about that? What's the u? 3x minus 9. If I replace the 3x minus 9 with the u, y would then be equal to what? U cubed. So dy du is equal to 3u squared, and du dx would be equal to what? 3. So from this, we can get dy dx, which would be equal to, this is the idea of combining steps, 3 times u squared times the 3, with u being 3x minus 9. All right? So all of that is going in the blank here. And once it does, you have your derivative. It's just a question of, do you want to simplify it a little bit just to make it fit? Might not be the worst idea in the world. So I'll write that as 9 times 3x minus 9 squared. And I'll write that in here. Green to box it. But this is my final answer.